Welcome! In this session, we'll explore an interesting binary tree problem titled Even-Odd Tree. Together, we'll break down the problem, review its requirements, and walk through an efficient solution step by step. Let's dive in and learn something new. An even-odd tree is a binary tree that adheres to specific rules based on the levels of the tree. First, it's important to know that the root is at level 0, and levels alternate between even and odd, starting with level 0 as an even level. Now, on even index levels, such as level 0, all nodes must have odd integer values, and the values must be strictly increasing from left to right. On the other hand, for odd indexed levels, all nodes must have even integer values, and their values must strictly decrease from left to right. The task is to determine if a given binary tree satisfies these conditions, and if it does, we return true, otherwise, we return false. The input to the problem is the root of a binary tree, where each node contains an integer value. The output is a Boolean value, either true or false, depending on whether the tree meets the even-odd tree criteria. Now, let's look at an example. Consider a binary tree with the structure shown. At level 0, we have the value 1, which is odd and satisfies the strictly increasing condition. At level 1, we see the values 10, 4, which are even and strictly decrease from left to right. Finally, at level 2, the values 3, 7 are odd and strictly increase. Since all levels meet the stated conditions, the output for this tree is true. This example demonstrates a valid even-odd tree. In another example, we have a tree where the root value is 2, and its child nodes are 12 and 8. Looking at level 0, the value 2 is even, which is invalid because the root level must have an odd value. Since the first condition is violated, the tree does not satisfy the even-odd tree requirements, and the output is false. This highlights how a tree can fail the rules as early as the root level itself if the integer value does not meet the criteria for that level. In a final example, the tree has a root value of 5, with child nodes 9 and 1 at level 1, and further nodes 3 and 5 at level 2. At level 0, the value 5 is odd, which is valid. However, at level 1, the values 9, 1 are both odd, which violates the condition that all nodes at odd index levels must have even values. This makes the tree invalid as an even-odd tree, and the output is false. The constraints of the problem also specify that the tree can have up to 100,000 nodes, and values can be as large as 1 million, so the solution must be efficient. Additionally, edge cases like a single-node tree or trees with only left or right subtrees must be carefully handled to ensure correctness. To determine if a binary tree satisfies the conditions of an even-odd tree, we need to evaluate the tree level by level based on two key rules. First, for nodes at even index levels, starting from level 0, the values must be odd and strictly increasing. Second, for nodes at odd index levels, the values must be even and strictly decreasing. One approach to solving this is a brute force method using level order traversal, or BFS. In this method, we process nodes level by level and store their values in a list. For each level, we then validate the values by checking the constraints: odd values in increasing order for even levels, and even values in decreasing order for odd levels. This approach is straightforward but comes with certain inefficiencies, which we will explore next. The brute force approach has some notable drawbacks in terms of complexity. Time complexity is n squared, where n is the number of nodes, due to the extra work required to validate the values for each level after traversal. Space complexity is n, as we need additional storage to hold the node values for each level in lists. Moreover, storing all node values and then separately checking for the strictly increasing or decreasing conditions introduces redundancy. To address these inefficiencies, we can use an optimized BFS approach that eliminates the need for extra storage. In this optimized method, we validate the conditions directly during traversal. By keeping track of the previous node value as we process each level, we can ensure that each value satisfies the required constraints: odd and strictly increasing for even levels, and even and strictly decreasing for odd levels. If any condition fails, we terminate early and return false. Otherwise, we return true once all levels are processed. The optimized BFS approach significantly improves efficiency. Its time complexity is reduced to n, as each node is processed only once during the traversal. Space complexity remains n, due to the BFS queue, but no additional storage is required for intermediate lists of node values. This method offers several advantages. By validating values directly during traversal, we avoid the overhead of storing node values and performing redundant checks. This makes the approach more practical for large trees, as it minimizes both time and memory usage. For these reasons, the optimized BFS approach was chosen as the preferred strategy. It balances efficiency and clarity, ensuring that the solution is scalable and easy to implement while adhering to the problem constraints. There are some important observations that make the optimized BFS approach particularly effective. The alternating constraints, odd or even values in strictly increasing or decreasing order, can be validated seamlessly in a single BFS pass. The distinct properties of nodes at even and odd levels simplify the logic, allowing us to check conditions directly without intermediate storage. This realization was the aha moment that highlighted the unnecessary overhead of the brute force approach. When comparing the two strategies, the brute force method is easier to implement but consumes more memory and time, making it suitable only for small trees. In contrast, the optimized BFS approach is more efficient and scalable. While it introduces a slight increase in implementation complexity, it eliminates redundant operations and handles larger trees more effectively. Given these trade-offs, the optimized BFS approach strikes the right balance between time and space complexity, making it the most practical choice for this problem. To determine whether a binary tree is an even-odd tree, we start by using a breadth-first search, or BFS, approach. BFS is particularly useful here because it allows us to traverse the tree level by level, which is crucial for verifying the problem's conditions. We begin by initializing a queue with the root node, which helps us process one level at a time. Alongside the queue, we maintain a level index to track whether we're at an even or odd level. At each step, the queue holds all the nodes for the current level, and we continue processing until the queue is empty. For each level, we first record the size of the queue, which tells us how many nodes are in the current level. We then process each of these nodes by dequeuing them, storing their values in a list for validation, and enqueuing their children, if they exist, for processing in the next level. Once all nodes in the current level are handled, we validate the level's conditions. On even index levels, all node values must be odd and strictly increasing. Conversely, on odd index levels, all values must be even and strictly decreasing. If any level fails to meet its respective conditions, we immediately return false. Otherwise, we increment the level index and continue. If we finish processing all levels without issues, we return true, indicating the tree satisfies the even-odd tree conditions. This approach leverages BFS for its natural alignment with level order traversal. The queue ensures that nodes are processed in the correct sequence, making it easy to validate conditions level by level. Odd and even checks are efficiently implemented using modulo operations, checking whether a value is odd with value %2 = 1 or even with value %2 = 0. To ensure strict ordering within a level, we compare each node's value to the previous one. By maintaining a previous variable, we can efficiently verify whether values are strictly increasing or decreasing as required. The algorithm primarily relies on two data structures, a queue and a list. The queue is critical for BFS traversal, allowing us to store and process nodes level by level with constant time in queue and dequeue operations. The list, on the other hand, temporarily holds the values of nodes at the current level. This makes it easier to validate the level's conditions, such as checking for odd or even values and ensuring strict ordering. Together, these data structures provide a simple yet effective way to traverse and analyze the tree. To optimize the algorithm further, we can validate level conditions in real time while processing nodes, instead of storing all values in a list. This reduces memory usage and improves efficiency by eliminating the need for a separate validation step after processing the level. Additionally, edge cases need careful handling. For instance, a single node tree is always valid since the root node satisfies the odd value condition. For a tree with only one level, we just verify that all values on level 0 are odd. Finally, when dealing with potentially empty child nodes, we ensure that checks for left and right children are handled safely to avoid null pointer errors. The time complexity of this solution is O(n), where n is the total number of nodes in the tree. Each node is visited once, and level validation involves iterating through the nodes in the current level, ensuring systematic processing. The space complexity is determined by the maximum width of the tree, as the queue stores nodes of a single level at a time. This gives us a space complexity of O, W, where W is the maximum number of nodes at any level. Overall, this approach is both time-efficient and space-efficient, ensuring that all levels are validated methodically while minimizing resource usage. To implement the solution for the even-odd tree problem in Python, we start by importing the Deque class from the collections module, which will help us manage the nodes level by level. Inside the solution class, the isEvenOddTree method first checks if the root is null. If it is, the tree automatically satisfies the conditions, so we return true. Otherwise, we initialize a queue with the root node and set the level counter to 0. The while loop then processes the tree level by level. At each level, we record the number of nodes currently in the queue as level_size and initialize a variable prev_value to none. This prev_value will help keep track of the value of the previously processed node within the current level. Next, we enter a for loop that iterates through all the nodes in the current level. For even indexed levels, like level 0, 2, 4, and so on, we check two conditions: the node value must be odd, and it must strictly increase compared to the previous node in this level. If either condition fails, we return false immediately. The prev_value variable is then updated to the current node's value so that the next node in the level can be compared against it. After processing the current node, we check if it has left or right children. If it does, these children are added to the queue for processing in the next level. Once all nodes in the current level are processed, the level counter is incremented to move to the next level of the tree. This continues until the queue is empty, meaning all levels of the tree have been validated. If we pass through all levels without returning false, the function concludes that the tree satisfies the even-odd tree conditions and returns true. This algorithm ensures efficient level order traversal while enforcing the required constraints for both even and odd levels. Here, we start by defining the treeNode class, which represents each node in the binary tree. Each node stores an integer value, and has references to its left and right child nodes. Then, in the solution class, we implement the method isEvenOddTree that checks if the given binary tree satisfies the conditions of an even-odd tree. We first handle the base case where the root is null. In such cases, the tree is trivially valid, so we return true. After that, we initialize a queue to facilitate level order traversal of the tree, starting by adding the root node to the queue. We also initialize a variable level to keep track of the current level of the tree during traversal, starting from level 0. For each level, we determine the number of nodes to process using levelSize, since we need to evaluate all nodes at the current level before moving on to the next. We also use a variable prev_value to keep track of the value of the previously processed node at this level. As we process each node, we check the constraints of the even-odd tree. On even index levels, all node values must be odd and strictly increasing. If a node violates this rule, we return false immediately. Similarly, on odd index levels, all node values must be even and strictly decreasing. Again, if any node fails this condition, we return false. After evaluating the current node, we update prev_value and add the node's children to the queue, if they exist, so that we can process them in subsequent levels. Finally, we increment the level counter to move to the next level. After traversing all levels of the tree without encountering any violations, we return true, indicating that the tree satisfies all the conditions of an even-odd tree. This approach efficiently performs a level order traversal and validates the tree in n time, where n is the number of nodes in the tree, as each node is processed exactly once. In this example, we have a binary tree with 3 levels. Let's analyze if it satisfies the rules of an even-odd tree. We begin by initializing a queue with the root node, which is 1, and set the level to 0. At level 0, there is only one node, the root. Since the value of the root node is 1, which is odd, it satisfies the condition for an even-indexed level. We then add its children, 10 and 4, to the queue and move to the next level, level 1. Now, at level 1, the queue contains 2 nodes, 10 and 4. When processing the first node, 10, we see it is an even number, which is valid for an odd-indexed level. This means the tree remains valid so far. Next, we process the second node at level 1, which is 4. The value 4 is even, and since the values on this level must be strictly decreasing, this condition is also satisfied. After processing this level, we add the children of nodes 10 and 4 to the queue, which are 3, 7, 9, and 5, and move to level 2. At level 2, the queue contains 4 nodes. As we process these nodes sequentially, we observe that all values 3, 7, 9, and 5 are odd. Additionally, these values are strictly increasing, which satisfies the conditions for this even-indexed level. With the queue now empty and all levels validated, the final output for this tree is true. In this second example, we analyze a tree with 3 levels but encounter a violation of the even-odd tree rules. We start with the root node, 5, at level 0. Since 5 is odd, it satisfies the condition for an even-indexed level. We then add its children, 9 and 1, to the queue and move to level 1. At level 1, the queue contains 2 nodes, 9 and 1. When processing the first node, 9, we notice it is odd, which violates the condition for an odd-indexed level. At odd-indexed levels, all nodes must have even values. Because this violation occurs, we immediately stop further processing and return false as the output for this tree. In this final example, we have a tree with only a single node, which represents an edge case. The root node has a value of 2, and we start processing at level 0. Since there is only one node, the level size is 1. However, the value 2 is even, and at even-indexed levels, node values must be odd. This violates the even-odd tree rules, so we immediately return false as the output for this tree. The time complexity of this solution is O(n), where n is the number of nodes in the binary tree. Let's break this down step by step. First, the algorithm uses a breadth-first search, or BFS, to traverse the tree. In this approach, each node in the tree is visited exactly once, which means the traversal itself contributes O(n) to the overall time complexity. Next, at each level of the tree, the algorithm performs a constant amount of work for each node. This includes checking if the node's value is even or odd, which takes O(1), and comparing it to the previous value on the same level, which also takes O(1). Since these operations are repeated for every node without adding any additional overhead, the combined work across all levels remains proportional to O(n). Therefore, the total time complexity for the entire algorithm is O(n). Now, let's analyze the space complexity, which is O(w), where W represents the maximum width of the binary tree, or the maximum number of nodes at any level. To understand this, consider the queue used for the BFS traversal. This queue temporarily stores nodes level by level as the algorithm processes the tree. The peak memory usage for the queue occurs when it holds all the nodes at the level with the maximum width. For a balanced binary tree, this maximum width occurs at the last level, which can contain up to n/2 nodes, giving a space complexity of O(n). On the other hand, for a skew tree where all nodes are aligned in a single branch, the width is always 1, resulting in O(1) space for the queue. Additionally, the algorithm uses a few temporary variables like level_size, prev_value, and level, but these only require O(1) space and don't impact the overall complexity. As such, the total space complexity is O(w), which simplifies to O(n) in the worst case. Let's consider the best, average, and worst case scenarios for this algorithm. In the best case, the binary tree contains just one node, the root. Here, both the time complexity and the space complexity are O(1), since there are no levels to traverse or nodes to store. In the average case, for a balanced binary tree, the time complexity remains O(n), because all nodes are visited, but the space complexity improves to O log n, since the queue only needs to store nodes level by level, and the number of nodes at each level decreases logarithmically. For the worst case, in a complete binary tree, the time complexity remains O(n), but the space complexity becomes O(n), because the last level has the maximum number of nodes, which is proportional to the total number of nodes in the tree. Comparing this BFS approach to a naive depth-first search, the BFS approach avoids redundant computations and additional storage for recursion stacks. It efficiently processes nodes level by level and uses a queue to achieve optimal time and space complexity of O(n). Finally, from a big O perspective, each node is visited exactly once, contributing O(n), and the queue stores at most one level at a time, contributing O(w). Therefore, the overall time complexity is O, n, and the space complexity is O, w, which simplifies to O, n, in the worst case when w equals n. When solving the even-odd tree problem, there are several common mistakes to be aware of, starting with the confusion between 0-based and 1-based indexing for levels. The problem explicitly uses 0-based indexing, so levels begin at 0, not 1. If you mistakenly assume a 1-based index, you might end up checking conditions for the wrong levels, such as enforcing even numbers at odd levels. To avoid this, always verify the level index during traversal and clearly distinguish between odd and even levels. Another frequent issue is neglecting the strictly part of the increasing or decreasing constraints. For example, using equals or equals in comparisons instead of or can lead to false positives when values are equal across levels. Always ensure your comparisons enforce strict conditions. Lastly, edge cases like an empty tree or a tree with only one node may be overlooked, resulting in runtime errors. These cases should be explicitly handled, such as returning true for an empty or single node tree, as they inherently satisfy the problem's requirements. Another common pitfall is assuming all integers are valid without checking the odd or even constraints for node values. For instance, failing to verify that odd levels contain even values and even levels contain odd values can lead to false positives. To prevent this, include explicit modulo checks, such as value %2 == 0 or value %2 == 1, for every node during traversal. Efficiency is another area where some solutions fall short. Using unnecessary nested loops or repeating level traversals can increase time complexity. Instead, leverage a queue for breadth-first search, or BFS, to process each level in a single pass. Additionally, this problem highlights several key insights for interviews. BFS is the preferred approach for clarity and efficiency when processing the tree level by level. While depth-first search, or DFS, can work, it tends to make level-based checks more complex. Modular arithmetic is crucial for ensuring odd and even constraints are met, and edge cases are often tested by interviewers, so handling scenarios like single-node trees, all even values, or duplicate values is essential. Finally, it's vital to strictly follow the problem's constraints, such as enforcing strictly increasing or strictly decreasing conditions without shortcuts. This problem is closely related to other tree traversal questions that you might encounter. For instance, binary tree level order traversal, LeetCode 102, provides the foundational understanding of level order traversal. Binary tree zigzag level order traversal, LeetCode 103, introduces similar constraints with additional complexity. Check completeness of a binary tree, LeetCode 958, focuses on validating the structure of the tree, and symmetric tree, LeetCode 101, emphasizes traversal alongside property validation. There are also alternative approaches to solving the even-odd tree problem. One option is using DFS with depth tracking instead of BFS. In this method, you recursively check level constraints while passing level information in tracking state. However, this can lead to higher memory usage, especially for deep trees. Another option is iterative BFS combined with array storage. Here, you store values from each level in an array and validate the constraints after traversal. This approach separates traversal from validation but increases space complexity due to the additional array storage. Each method has its own trade-offs, so you can choose the one that best suits your needs. To summarize, BFS is the most efficient and clear approach for solving the even-odd tree problem. During traversal, always validate both the odd/even constraints and the strictly increasing or decreasing conditions at each level to ensure correctness. Thoroughly test edge cases, including empty trees, single-node trees, or trees with duplicate values, as these are common scenarios interviewers might test. Lastly, optimize your traversal logic to avoid redundant computations, ensuring your solution is both efficient and robust. Great job! To wrap up, we've covered the even-odd tree problem, summarized its key concepts, and reviewed the algorithm's efficiency. We hope you found this walkthrough engaging and informative. Be sure to practice similar problems to strengthen your understanding. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!